Okay, so we're looking at this problem that's part of Chapter 13. It's 13.8, and it's the example, and it's the check your learning one. All right. Problem is we're going to have difficulty getting these numbers exactly to go backwards, so I was going to expand on it some and explain what the heck's going on here. All right, so we're just going to build the problem from how it's written. So we have our moles of iodine and hydrogen in a 1 liter flask, and we have a equilibrium constant of 50.5. So I am going to start up with an ice table. And I have the initial concentrations, just going to divide by 1, so this is 1 molar, and this is 2 molar, and this must be 0. So our change must be going forward. So at equilibrium we'd have 1 minus x and 2 minus x, and this is just going to be 2x. And our equilibrium equation is the hi squared over h2 and I2. All right, now the reason this problem arose, or what we're looking at here, is someone noticed that if we work backwards using the answers given, so what I mean by that, if I try to solve for k, if I take that 1.88 and square it, and then divide by both the h2, which is 0.06, and the I, which is 1.06, I don't necessarily get the k of 50. I actually get 55. All right, I'm going to solve this what I would call the right way and explain what the problem with these values is, because it turns out it's that one right there that's creating all the issues. And technically it is correct how they've written it. All right, so let me explain what the heck's going on with this. All right, let's solve it the right way. And this one would turn into a quadratic equation. So let's actually figure out what the quadratic is, and then I'm also going to show you how to solve it just from this right here. So right now I'm going to change color, because if I solve this the challenging way, I'm going to FOIL this and bring it up to the left side. So 1 times 2 is 2. 1 times x, and 2 times x is minus 3x, and then x squared. So I just FOILed that. And this is going to be equal to 4x squared. All right, so I'm going to do 50.5 times 2 and get 101 minus 50.5 times 3, 151.5 x, and this would be 50.5x squared, and I'm going to bring this over, so 50.5 minus 4. So when I just bring that over, that drops that down, and I get positive 46.5x squared. So I have my A, my B, and my C term. I'm going to figure out my b squared minus 4ac first, and a, b, and c. So 151.5 squared minus 4 times a, 46.5, times c, 101. And I get, under parentheses is 416, so I'll go ahead and take the square root of that. So this becomes negative, and I'll flip that sign, so positive 151.5 plus or minus 64.5 all over 46.5 times 2, 93. And we have our two roots possible. So I'm going to do plus first. So 151.5 plus 64.5, and then divide by 93, and I get a root of 2.32, and then 151.5 minus 64.5, and I get 87 divided by 93. My second root is 0.935. All right, that first root doesn't work because we'd end up with negative values for the H2 and the I2. So our x is this 0.935. And 1 minus 0.935 does round to 0.06, which is where this came from. But I imagine if we went back and instead checked this with 0.064, you'd get closer to that 50.5. Mathematically, what's happening is that is taking us down to one significant figure, and losing all that accuracy is why the Q and the K don't match when you try to plug it in. But I can't do that here. This was 1.00, and if I do 1.00 minus that, I only get to the 6, and then the rest is insignificant. So significant figures wise, this is a correct answer. Unfortunately, given you the chance to work backwards, you don't get the exact same Q as your K. All right, now I did say we're going to back up here and solve this using this equation as well. It's just another way of getting our x's. But if you have access to something like a TI, like this one, we actually can plot this equation. And I'm just going to turn this fraction into my equation. So 2x squared. And then I'm going to put this next, 1 minus x. But you notice I didn't do the divide symbol. I'm putting this in to say I want it at the bottom, followed by this. Also on the bottom, and then I need to move the 50.5 to the right, so I'm going to minus 50.5, and then just to make sure it works, I hit graph. And I don't necessarily care about the graph, but where it crosses 0 is important. Now technically I know one of them is probably the 0.9 and the other one's around 2, but I want to know exactly where it is, so I'm going to calculate the 0. Now on this you can calculate both zeros, but I only really care about one of them. I know my x that I care about is larger than 0, so I'm going to set my left bound at 0. And the largest it could be is 1, because if it was bigger than 1, this would become negative. So I just move my right bound up until I have a value larger than 1. And then I'm going to back up and put my guess at 0. And blah, 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 0.935. No, 935 with rounding. Get the exact same value as the quadratic equation had. But theoretically quicker once you get used to your graphing calculator. But still, the problem that that some of my students were seeing is that plugging these values in and working backwards give you a different answer. Had to do with a lot with significant figures, decreasing the precision in our calculation. Yet had to do it this way. So it is only one significant figure in the H2, but that's just the result of the math.